Hi there. My name is Aaron Lanchman. I'm a professor of electrical and computer engineering at Georgia Tech. I would like to close out this section of ECE2026 Introduction to Signal Processing on Z-transforms and FIR filters by taking a look at some example movies on the DSP First website. In all of these demo movies, the system function is shown in the upper right-hand corner. Since these are FIR filters, you can just read off the filter coefficients B sub k. Here they're 1, -2, and 1. And because these are FIR filters, those filter coefficients directly correspond to the values of the impulse response. In the upper left-hand corner, we have a pole zero plot. Now, because these are FIR filters, all the poles will be at the origin, so they're not very interesting. And over here, we have magnitude and phase plots for the frequency response. So to start with, we have two poles at z equals 1. So that's an angle of 0. So that corresponds to the frequency of 0. So we get a null at DC. Now, as we let the movie progress, we start to march the zeros along the unit circle. So we can see the nulls moving in the frequency response as well. Now, in the starting case here, if we think about moving along the unit circle and investigate what's happening at z equals -1, which corresponds to e to the j pi, or e to the minus j pi, we see that we're far away from that 0. So we have the greatest magnitude response over here. Now, when we hit this particular point, where the zeros now land at points corresponding to omega hat equals pi over 2, we see a null in the appropriate location. And I should mention that this x-axis is the normalized frequency of omega hat divided by 2 pi. So pi over 2 divided by 2 pi is 1/4, which corresponds to the 0.25 here. So we continue marching along, and then we hit this particular point where now both of these zeros are at z equals -1. That corresponds with a frequency of omega hat equals pi or minus pi. So we zero out that highest frequency. And now the point on the unit circle corresponding to DC is as far away as you can get from the zeros, so you get a peak here. So this is now a distinct low-pass filter. Now the rest of the movie is going to scoosh it in a little bit. So now it's hard to see on this particular plot, but it doesn't go all the way down to 0 here now. It's not a perfect null. And now the zeros are going to sort of reverse in direction, but they're going to stay off the unit circle like this. So we see that the dips don't go all the way down to 0. These aren't perfect nulls. Notice in this particular case, the value of the magnitude at DC and the value of the magnitude at omega hat equal pi, those are the same because the distance between this point on the unit circle and the zeros is the same as the distance from this point on the unit circle and the zeros. Okay, let's play the rest of it. And you see that this endpoint here has a case where the zeros aren't exactly on the unit circle. So when we look at this high-pass filter, this doesn't go all the way down to 0 at DC. What else does this website have in store? So let's see, it's starting out with this coefficient pattern of 1, -1, -1, 1. You can see that in the impulse response here. And it has two zeros here that are going to follow the same path that they did in the last demonstration, except we've added a third zero that's going to stay fixed at z equals -1. So regardless of what else happens, you'll have this null at omega hat equals pi. So they're moving around there. They come in like this. They then split off again, and then go back around the other direction. Let's see what it looks like at some of the particular points. Okay, that's what it looks like there. You can see that there's a lot being passed at DC because this point here is furthest from those zeros. Do-de-do-de-do. Now we have a very wide valley at omega hat equals pi because we have 3 zeros at one location. And then they split off like this. Maybe I need background music. So this plot here at the very end looks a lot like this plot here at the beginning, but the dips don't go all the way down to 0. And also notice we have 2 zeros on the right here. So the dip at DC is stronger than the dip at omega hat equals pi over 2 because you only have 1 0 over here on the left. Now is time on sprockets when we scroll downward. So in this particular example, the 0 on the right is going to be pulled inward along the real axis. Eventually it's going to hit the origin where it's going to cancel with one of the poles. So the little x here would change from a 10 to a 9. Let's play that. I realize this is not the most compelling video in the world. Not going to be competing with Mr. Beast anytime soon. So we see that the impulse response that it winds up with corresponds to a running sum. So the frequency response is a digital sync, aka aliased sync, aka Dirichlet kernel. You can see the nulls of the aliased sync corresponding to the angles of the zeros, and we have this big peak in the middle because we don't have a 0 here. You can compare this magnitude response with these decreasing side lobes, with this initial case with the 0 out here, where the side lobe heights are decreasing with omega hat, but it's barely noticeable. And there is this main lobe, although it's not as strong relative to the side lobes as in the actual aliased sync function. Let me start that again, and I'll stop it at another special case. There it is. If I imagine taking this system function and setting it equal to 0, I will get z to the 10 equals 1. So the solutions to that correspond to roots of unity. So I have zeros equally spaced around the unit circle. This kind of filter is referred to as a feed-forward comb filter. Later we'll look at feedback comb filters. And looking at the frequency response, you can guess why it's called a comb filter. Okay, one more example. This is like the previous example, except we're going to keep the 0 corresponding to DC fixed here on the unit circle, and we're going to take this conjugate pair of zeros and pull them towards the origin while keeping them at the same angles. So you should keep your eye on these peaks. So you see those peaks decreasing and then going back up. Notice we started out with 10 poles at the origin, but at the end here, the 2 zeros canceled with 2 of the poles, leaving 8 poles. Let me start it again, stop it right here. So this particular snapshot corresponds to the exact feed-forward comb filter we saw in the last example, but the rest of it is different. Although we could make the same qualitative observations about the main lobe and the side lobes. This snapshot is interesting because there's a definite main lobe here, but you see there's this tiny dip at what would otherwise be the peak of the main lobe. That's kind of interesting. Okay, I think that's enough for today.